All right, let's get right into it. Today, we are asking one of the biggest questions out there. What is our universe really made of? We're going to dive into a pretty radical new theory, one that might just flip everything we think we know on its head. Modern cosmology has this giant hole in it. See, everything we can actually see and touch, all the stars, the galaxies, you, me, that's only about 5% of everything. The other 95%, it's a total mystery. We've given it names, sure, dark matter and dark energy, but what if they aren't things at all? What if we've just been misunderstanding the very fabric of space this whole time? Okay, so this graph right here, this is the smoking gun. It's the whole reason we started looking for dark matter in the first place. The blue line shows how fast stars should be moving based on all the stuff we can see in a galaxy. They ought to slow down way out on the edges, but they don't. The red and black dots show what we actually see. They're just zipping along at crazy speeds. The only way that makes sense with our current rules of gravity is if there's a huge, invisible halo of something, giving them an extra gravitational kick.
All right, so to explain that weirdness and a bunch of other cosmic puzzles, scientists came up with what we now call the Standard Model of Cosmology. It's been a huge success, and it goes by the name Lambda CDM.
So what exactly is Lambda CDM?
Well, the name kind of gives the game away. That Greek letter, lambda, stands for dark energy. That's the mysterious force that's making the universe expand faster and faster. And CDM? That's for cold dark matter, the invisible glue we think is holding galaxies together. This framework is, for all intents and purposes, the bedrock of modern cosmology.
Let's just break that down for a second. The universe, according to this model, is about 70% dark energy and 26% cold dark matter. That leaves our normal stuff, everything we know and love, at just 5% of the whole pie. And look, this model is really good. It perfectly predicts the patterns in the afterglow of the Big Bang, how galaxies clump together. It just works. But here's the catch. Its biggest successes rely on two things we've never actually found and, frankly, don't really understand. But what if there's another way to look at all this? An idea that doesn't need to invent mysterious new things to fill in the gaps. Well, this is where a new challenger steps into the ring. It's called Dynamic Vacuum Field Theory, or DVFT for short. Now, the central idea behind DVFT is a total game changer. It says that what we call empty space, the vacuum, isn't empty at all. Not even close. It's a real physical thing, a dynamic medium. You could almost think of it like a superfluid or maybe a super stiff gel that fills everything. And in this theory, things like gravity and even the expansion of the universe aren't just extra ingredients. They're just what this vacuum does. And this chart really lays out the core difference. In the standard model, space is just a passive stage where everything happens. And to make the cosmic play work, you have to add these two mysterious actors, dark matter and dark energy. But in DVFT, the stage is the main character. The vacuum is an active, physical medium, and its own properties create the effects that we've been blaming on those dark components. You don't need the extra actors. So how in the world can the vacuum do all that? Well, the theory says it has a property called stiffness or coherence. The best way to picture it is like a single, incredibly rigid web stretching across the entire universe. If you pluck it in one corner, the vibration is felt everywhere, almost instantly, because it's just that stiff. It's this coherence, this interconnectedness, that lets the vacuum coordinate things over huge cosmic distances, and that's where all its explanatory power comes from. Okay, so we've got our two contenders. In one corner, the reigning champ, Lambda CDM, and in the other, the upstart challenger, DVFD. Let's put them head-to-head and see how they handle the biggest puzzles in cosmology.
Round 1. We go right back to the problem that started this whole thing. Those stars at the edge of galaxies spinning way too fast. How do our theories explain it?
So Lambda CDM's answer is pretty straightforward. Just add more stuff. It proposes a giant invisible cloud of cold, dark matter particles that surrounds the galaxy, providing the extra gravity needed. DVFT's answer is, well, it's way more profound. It says, nope, no new particles. Instead, the vacuum itself just behaves differently out there on the fringes of a galaxy where accelerations are super low, and that change in behavior creates a force that looks exactly like dark matter. And here you can see that idea in action. This is real data from a galaxy called NGC 4157. The blue dots are the speeds we actually measure, and that red line? That's what DVFD predicts using only the visible stars and gas. And look at it. It's a perfect fit. No dark matter needed, not a single particle. All right, Next up, the horizon problem. This one's a classic. When we look at the oldest light in the universe, the cosmic microwave background, it's the same temperature everywhere. I mean, astonishingly uniform. But here's the thing. In the standard model, chunks of the early universe were so far apart they can never have been in contact. So how did they all get the memo to be the exact same temperature? The standard answer is something called cosmic inflation. It's this idea that for a split second after the Big Bang, the universe expanded way faster than the speed of light, taking one tiny uniform patch and stretching it out to become our entire cosmos. DVFT, though, has a much simpler answer: vacuum coherence. Remember that cosmic stiffness? It means the whole vacuum was basically locked together from day one. It didn't need a period of hyperexpansion to smooth things out, because the universe was born uniform, held in perfect sync by the rigid fabric of space itself. You know, talk is cheap, right? Especially in theoretical physics. A theory is only as good as its predictions. It has to match what we actually see out there. So let's see how our two contenders stack up against real observations from the cosmos. And the ultimate test, the gold standard for any theory about the universe, is the cosmic microwave background, the CMB. You can think of it as the universe's baby picture, a snapshot from when it was only 380,000 years old. It is packed with clues about how everything works. Any legit theory of everything has to get this picture right. And this is what that baby picture looks like when you turn it into data. It's called the CMB power spectrum. All those peaks and valleys basically show us the fossilized sound waves that were sloshing around in the early universe. For a theory to have any shot at being right, it has to predict the exact location and height of every single one of those bumps. So how does DVFT do? Well, it does incredibly well. Just look at the scorecard. It nails the main peaks, the first, the second, all of them, just as perfectly as the standard model. But then it does something extra. See, the standard model has always had a little trouble with the data on the far left, at the very largest scales in the sky. DVFT, because of its whole vacuum coherence thing, actually predicts a 10% boost in power right there, which could explain that nagging anomaly. And it also predicts a slight dip on the far right, which gives us a unique signature we can go look for. This image shows you that unique fingerprint. While Lambda CDM does an amazing job through the middle, DVFT makes these very specific, different predictions at the extremes. And that's exactly what you want from a new theory. You don't just want it to explain what we already know. You want it to make new predictions that we can actually go out and test, predictions that could prove the old theory wrong. And the challenges to the standard model aren't just from ancient light. The James Webb Space Telescope is giving us brand new headaches. It's looking back to the cosmic dawn and finding these huge, well-built galaxies that honestly shouldn't exist that early on. The standard model predicts a much slower, gradual buildup. But DVFT might have an answer. It sees the Big Bang as a kind of phase transition in the vacuum, one that would inject a ton of extra energy into the early universe, giving galaxy formation a massive head start. It actually predicts the kind of early cosmic boom that Webb is now seeing.
So, where does that all leave us? On one hand, we've got the standard model. It works beautifully, but it's held together by these mysterious placeholders. And on the other, we have this challenger that seems to explain all the same stuff, and maybe even a little more, by completely rethinking what space itself is. We could be at a real turning point here.
Let's look at the final tale of the tape. For every big puzzle where Lambda CDM needs to invent a new exotic thing, dark matter, dark energy, inflation, DVFT has an explanation that comes directly from the physical properties of the vacuum. It even gets rid of the Big Bang singularity, that point of infinite density where all of our physics just breaks. The bottom line is this: DVFT seems to replace placeholders with actual physical mechanisms, and it makes its own unique predictions we can test. And that really brings us to the final mind-bending question. For decades, the hunt has been on for new particles to solve these cosmic mysteries. But what if the answer isn't out there in some exotic new type of matter? What if the revolution we've been waiting for has been right here, all around us, hidden in the strange, dynamic, and powerful nature of what we've always just called empty space?